Hello, this is Yanxie, and here's my report for Lab 3. The goal for this lab is to measure the distance dependence on the magnetic field due to a small bar magnet. Some fundamental principles that are involved in this lab include the Biot-Savart law and the distance dependence relationship of a bar magnet. The procedures for this lab are as followed. First, we need to download a magnetometer app. In this experiment, I used the app Teslameter. Second, we need to line up the smartphone with north to compensate for magnetic north. Third, we locate the magnetometer chip in the phone for more precise measurements. Finally, we find a distance from the magnet to the sensor that produces a magnetic field with Bx equals 20 microtesla. We record this distance and this value of Bx. We repeat this final step for distances R70, R120, R170, and R220. By the end of this lab, I've calculated the distance dependence to be negative 2.7804 and the magnetic moment to be 3.2836 am squared. This slide presents the data table and graph for my measured distance values and magnetic field values. The graph on the right can be represented by the equation ln of the magnitude of Bx equals negative 14.236 minus 2.7804 times ln of r. Using the known relationship of distance dependence to a bar magnet, we obtain the value of ln k to be negative 14.236 and the value of distance dependence to be negative 2.7804. Then we could calculate the magnitude of the magnetic moment, which is 3.2836 am squared. This slide presents my off-axis data with an average experimental magnetic field at 45 degrees to be 1.533 e to the negative 5, 7.21 e to the negative 5, 1.8 e to the negative 5 Tesla. Throughout my experiment, I noticed that when the magnetometer is far away from the magnet, it measures a near-zero magnetic field in the x direction. In addition, as the magnetometer moves closer to the magnet, the measured x component of my magnetic field increases. The first portion of code sets up the physical constants and creates the magnet at the origin. The segment of code in the middle creates a function for the magnetic field using Biot-Savart law. The piece of code on the bottom sets up 2 on-axis observational locations and 4 observation locations perpendicular to the axis. This piece of code draws 2 arrows to represent the magnetic field on axis. This piece of code draws 4 arrows to represent the magnetic field perpendicular to the axis. On the top, I inserted the average D perpendicular from my experiment. On the bottom, the code draws an arrow to represent the magnetic field 45 degrees from the axis. Here is the output of my code. The magnetic field at 45 degrees computed by my model is 1.2538 e to the negative 5, 3.76141 e to the negative 5, 0 Tesla, as compared to my experimental magnetic field at 45 degrees, which is 1.533 e to the negative 5, 7.21 e to the negative 5, 1.8 e to the negative 5 Tesla. If I hadn't oriented my experiment to compensate for magnetic north and had instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field, I would not be able to get the correct result, as it would be impossible to identify or separate the magnetic field exerted by the Earth and the magnetic field exerted by the magnet. If I were to stick 2 identical magnets together end to end and run the experiment again, I would expect the magnetic field to increase in the same direction, and that concludes my report. Thank you.